Welcome back, everyone, to the deep dive. Today, we're going on a journey, a fascinating one actually, into the evolution of building documentation. That from the very first structures humans ever built to what's happening right now at the cutting edge.
Sounds ambitious.
It is, but you gave us some really amazing sources to dive into. A brief overview of the history of CAD, which is fantastic for giving us the timeline of design technology, the Wikipedia entry for history of CAD software to see how the software itself developed over time, and then a presentation. It's called History of Building Documentation and the BIM Future.
Ah, that last one, that's really going to tie it all together.
Exactly, because it focuses specifically on how these changes have impacted the building industry, culminating in, where we are now with BIM,
Yeah.
building information modeling. So for our listeners who are, well, they're already interested in this stuff, right? They follow the show. We're going to extract the key insights. We're going to see how we went from drawing by hand to CAD, and then how BIM is transforming the entire way we design and construct buildings.
It's remarkable when you lay it all out, how much has changed and how quickly. And for those who are maybe less familiar with the details, we're going to make sure those aha moments happen along the way. We don't want to get bogged down in too much technical jargon, though. Right. We want to keep it accessible but insightful. So let's go way back. Before computers, before even blueprints were common, before the 15th century, building was more of an art than a science in a way. There weren't the formal engineering drawings that we're used to. It was all about the master builder.
Yeah, the master builder and their experience, they were the ones who held all the knowledge.
Think about like the Greek Parthenon.
Yeah.
Incredible structure built with such precision.
Yeah.
And we don't have detailed blueprints from back then, but clearly they had some pretty sophisticated methods of calculating and documenting. Just wow, how did they do it?
It's fascinating to think about, right? The level of understanding they must have had of geometry and material properties, even without those dimension drawings we rely on today. Right. I mean, it was probably passed down through apprenticeships, years of training, the skills of the craftsmen themselves embodying that knowledge. So in a way, the documentation was the craftsman.
Exactly. It was a different form of documentation, less about written plans and more about embodied knowledge. But information was definitely being conveyed and applied, just in a different way.
Right. And then around the 15th century, things start to shift, particularly in Italy. We start to see graphic projections become a more common way for architects to communicate. And paper starts to replace parchment. I mean, that alone must have been a big deal.
Huge, more practical, more affordable. It would have made it so much easier to create and share designs. And the sources do mention, we do have engineering drawings from the 14th and 15th centuries.
Oh, really? I didn't realize they were that old.
Mostly sketches, though. Found in bound volumes in European museums. They weren't super precise in terms of like exact scales and dimensions.
More like conceptual, I guess.
Yes, but often with extensive textual descriptions alongside them. So they acted more like illustrated guides with accompanying notes,
Hmm.
more descriptive than prescriptive.
So it wasn't just about the visual, there was a lot of written information too. I wonder how much was lost in translation sometimes, relying on interpretation.
It definitely relied on a shared understanding between the designer and the builder. And it's interesting, these early drawings weren't just for construction. They were often used as presentation pieces for patrons, too. Imagine showing off a beautifully rendered sketch to secure funding for a project.
It's like the early version of those architectural visualizations we see today, right? But with pen and ink instead of computers.
Exactly. And for the builders themselves, because each project was so unique back then, those drawings were more like a visual language they shared. These were experienced craftsmen. They didn't need a precise measurement for every little detail.
They understood the intent, the overall concept. And that's something that our source highlights with Leonardo da Vinci's work, which, while incredible, wasn't quite what we'd consider a technical drawing today.
Right. His sketches were very innovative for their time, and you could definitely use them to build from. But he wasn't using, for example, the multi-view projections that later became the standard in engineering drawing.
More artistic representations. And then we start to see this shift towards a greater emphasis on precision, standardization. In the 15th century, you have people like Leon Battista Alberti advocating for the use of like Euclidean geometry and multiple views in drawings.
That was a pivotal moment, really. It marked the beginning of a more analytical approach to design.
Yeah.
You're moving away from simply showing what something looks like to actually depicting how it's put together with geometric accuracy.
It's about communicating the underlying structure, not just the aesthetics. And this evolution really takes off with the development of descriptive geometry by Descartes and Monge. That lays the foundation for what we consider modern engineering drawing.
And then the Industrial Revolution kicks in. Suddenly you have this massive need to produce things at scale, to standardize components. That fuels a rapid evolution in engineering drawing practices throughout the 19th century.
So the drawings become even more critical to the whole process. It's not just about individual craftsmen anymore. It's about communicating complex designs to a larger group of people.
Absolutely. The drawings have to be unambiguous. Everyone needs to be on the same page. And it's interesting, even with this drive towards standardization, there were still some pretty significant regional differences in how drawing was done.
Oh, really? So even then, there wasn't a single universal standard.
Not quite.
Hmm.
For example, drafting practices on the European continent tended to be more technical, while English practices retained a stronger craft-based approach for quite a while. They were even using watercolors for highlighting drawings well into the early 20th century.
It's like each region had its own dialect of drawing. And speaking of standards, it's kind of surprising to learn that formal drafting standards weren't really a thing until after World War I.
Yeah, it's kind of mind-blowing when you think about it. The first American standard didn't come about until 1935. And before that, you can only imagine the potential for misinterpretations, errors, and just general confusion.
Right. You'd think with industrialization and mass production, you'd need that clarity from the get-go. And another big driver of standardization was the patent process, right?
Absolutely. If you wanted to protect your invention, you had to provide very specific standardized drawings. The Patent Office demanded clarity and consistency. It really pushed the development of more rigorous drawing practices.
It makes sense. You need to be able to replicate an invention precisely. And speaking of replication, before blueprints were widely used, just the act of copying these detailed drawings must have been a nightmare.
It was incredibly laborious. You're talking about highly skilled grafters, painstakingly copying lines and lettering by hand. It was a slow and expensive process. And even though the blueprint process was actually discovered relatively early, around 1840, it wasn't widely adopted right away.
Why not? It seems like such an obvious improvement.
It probably took a while for the technology to become reliable and affordable enough for widespread use. But once it did, it revolutionized the way drawings were shared and reproduced. It made collaboration so much easier and less expensive.
The sources really paint a picture of early drafting as this incredibly meticulous, almost artistic process. Meticulous pencil work, then inking over those lines on tracing cloth, and the lettering had to be perfect.
Oh, the lettering. There's a real art to it, often done with specialized tools like the Leroy lettering set, which was basically a set of templates and guides for creating perfectly uniform lettering.
It all sounds incredibly time-consuming and requiring a lot of skill and patience. And as engineering became more specialized, different disciplines developed their own drawing conventions, right?
Yeah, an architect's drawing is going to look different from an electrical engineer's drawing, which is going to look different from a mechanical engineer's drawing, and so on. And certain industries presented unique challenges. The source mentions the difficulties of creating 1.1 scale drawings for large components, like in the aeronautical industry.
Oh, wow. Yeah, imagine trying to lay out a full-scale wingspan on paper. You'd need a hanger just for the drawing board.
Practically speaking, it required specialized techniques and huge drawing surfaces. And after World War II, there was a real push to improve efficiency in drafting offices. So we see things like pre-printed stickers for repetitive details and more advanced reproduction machines to speed up the process.
All those little improvements adding up to big time savers. And let's not forget the mental gymnastics involved in design before computers. All those calculations done by hand, with slide rules and log tables. Our source even mentions Burrington's Handbook as an essential reference for engineers back then.
Ah, Burrington's, the engineer's Bible, filled with tables and formulas for everything you could possibly need to calculate. But it was a tedious process, prone to human error. You had to check and double-check everything.
And I bet there were a lot of late nights spent hunched over those calculations, so the arrival of computers must have felt like a huge relief.
Oh, absolutely. But it wasn't an overnight transformation. The very first computers, back in the mid-1940s, were mainly used for military calculations. Very specialized, very expensive.
Not exactly user-friendly, I imagine.
Not at all. But by the 1950s, large engineering companies started exploring how these massive machines could be used for more general problem solving. However, it was still a very indirect process. Engineers would prepare their calculations, which were then fed into the computer by specialized operators.
So there was still this disconnect between the engineer and the machine.
And the results would come back as numerical data, which often had to be manually plotted to create any kind of visual representation.
Mm.
It's a far cry from the interactive design tools we have today.
But even with those limitations, it was a step towards automating some of the more tedious aspects of engineering. And in the mid-1950s, early 1960s, we see the emergence of lower-cost computers like the LGP-30 and the IBM 1620. They weren't as powerful as the mainframes, but they were more accessible, and they allowed for more direct interaction.
And this period also saw the very early beginnings of what we might call commercial graphics systems. These were incredibly rare and expensive, though. It was really the giants of the automotive and aerospace industries, companies like Renault, Ford, and Lockheed, who pioneered this early work.
They had the resources to invest in this cutting-edge technology.
They did. They were using mainframe computers, mostly from IBM, and these things called vector refresh terminals, which were basically early graphical displays. And this is where we see the birth of some of the earliest CAD software, like CATIA, which came out of Renault's work on a system called Unisurf, PDGS from Ford, and CADAM from Lockheed. These weren't off-the-shelf products, they were custom-built systems tailored to very specific needs.
So the very first CAD systems were essentially in-house projects at these big companies. And it wasn't until 1969 that we see the emergence of a true commercial CAD industry, with companies like Applicon and Computer Vision entering the market.
And they were quickly followed by others, companies like Autotrol, Calma, and Intergraph. These early commercial systems moved away from the mainframes to smaller, more affordable mini-computers. They were using a different display technology called storage tubes, which were cheaper but had some limitations. And the initial focus was heavily on 2D drafting, particularly for the electronics industry.
It's interesting that the early focus was on electronics. You'd think mechanical engineering, with all its complex parts, would have been the driver.
Maybe. But the complexity of electronic circuits, especially as they started to get miniaturized, really demanded a more precise and efficient way to design and document them. And these systems were still a major investment. Our source mentions a price tag of around $150,000 in 1972 for a single CAD workstation.
Wow, that's a serious chunk of change.
It was. But the selling point was the potential for cost reduction. The idea was that you could automate a lot of the drafting tasks, which meant you needed fewer manual drafters. And for repetitive work, the productivity gains could be substantial. Many of these early systems also incorporated user-friendly programming languages, which allowed companies to further automate their workflows.
So the potential was there, but it was still early days.
And there were still significant technical hurdles. System performance was a major challenge. Those early computers weren't nearly as powerful as what we have today.
And from 2D, the obvious next step was 3D. But as our sources point out, those early attempts at 3D CAD using wireframe geometry had some limitations. It was basically just drawing the edges of an object. You didn't have the surface information needed for realistic rendering, or even for things like automatically hiding lines that shouldn't be visible.
It was a very abstract way of working in 3D. You had to sort of imagine the surfaces that weren't actually being displayed.
Yeah.
And the real push towards more sophisticated 3D modeling came from industries like automotive and aerospace.
Where those complex curves are so important.
Exactly. And that's where we see the development of surface modeling techniques. There were some key innovations like Kuhn's patches, developed at MIT, and Bezier curves and surfaces, pioneered independently by Citroën and Renault.
A lot of this early work was happening in the research labs of these companies.
It was. And Renault's early work with Unisurf eventually became a core part of CATIA. And then you have academic research building on these foundations, leading to things like B-splines and NURBS, or non-uniform rational B-splines. Ken Verspril at Syracuse University is often credited with formalizing NURBS, which have become a fundamental part of 3D modeling.
So even in the early days of CAD, we see this interplay between academic research and commercial application. It's like a feedback loop, each pushing the other forward.
Absolutely. And companies like Boeing, which were early adopters of these 3D modeling techniques, also became strong advocates for interoperability standards, like IGS. That was crucial for ensuring that different CAD systems could exchange data.
Because you don't want to be locked into a single vendor's ecosystem.
right? You need that flexibility. And parallel to the development of surface modeling, we see the emergence of solids modeling in the late 1960s and early 1970s.
So instead of just representing the surfaces of an object, you're actually modeling the solid volume it occupies.
Exactly. There were some key research groups and projects pushing this forward. The CAD group at Cambridge, their work eventually led to the ACIS and parasolid geometric modeling kernels, which are still widely used today.
It's amazing how much of the foundation of modern CAD was laid back in those early research efforts.
It really is. And then there was Emirdi's Synthovision system, which was notable for its early commercial success. It was even used in the movie Tron, and the production automation project at the University of Rochester, which developed the Paddle 1 and Paddle 2 solid modeling languages. It took a while for solids modeling to become truly robust and commercially viable, but by the late 1980s, it was starting to take off.
And the 1980s also marked a big shift in the CAD landscape with the rise of engineering workstations. Companies like Apollo, Sun, and SGI were offering more powerful computing at lower cost than those traditional mini-computer-based systems. And they embraced standard hardware and networking, which put a lot of pressure on those established CAD vendors who were still tied to proprietary solutions.
It was a disruptive moment. Suddenly, the playing field was more level. And then, of course, came the personal computer.
The game changer.
The IBM PC, introduced in 1981, truly revolutionized the industry. Companies like Autodesk, with the launch of AutoCAD in 1982, were offering a significant portion of the functionality of those high-end systems, but at a dramatically lower price. And they were selling it as software only, distributed through a network of dealers. It was a completely different business model.
More accessible, more affordable. It really democratized access to CAD technology.
It did. And the major CAD vendors, they initially underestimated the impact of the PC. They thought it was just a toy.
Classic disruption story.
But they were forced to adapt. By the mid-1990s, with the increasing power of PCs and the rise of operating systems like Windows NT, the PC had become the dominant platform for CAD.
And just as the industry was adapting to this new landscape, another key innovation emerged: feature-based parametric design.
Pioneered by Parametric Technology Corporation with ProEngineer in 1987, it changed the way engineers thought about modeling. Instead of just drawing lines and surfaces, you were defining intelligent features with associated parameters.
So the design became more dynamic, more adaptable.
Exactly. If you change one parameter, like the diameter of a hole, any related features would automatically update. It was the much more powerful way to work, and it forced the rest of the CAD industry to rethink their approaches. And then in the 1990s, we see the rise of what we might call mid-range CAD systems, things like SolidWorks, Solid Edge, and Autodesk Inventor.
Tailored to that PC environment.
They were. They used component software architectures, which made them more flexible and customizable, and they were sold through dealers at more accessible prices. And over time, through acquisitions and internal development, these mid-range systems have become increasingly sophisticated, and their capabilities have converged somewhat with those of the high-end systems.
It's like the lines have blurred between what used to be distinct categories. So now we're at the present day, and we have to talk about building information modeling, or BIM. Our presentation source makes a very strong case that BIM isn't just the future, it's very much the present of building documentation. And it gives this really fascinating historical overview to put things in context.
It does. It points out that 200 years ago, drawings were entirely manual, architects and engineers were often the same person, construction timelines were much longer, and materials were often procured as needed on site. It was a very different world. Think back to the era of someone like Sir Christopher Wren.
Yeah, those iconic buildings designed and built without the tools we take for granted today. And then fast forward 100 years, drawings are still largely hand-produced, but the architect and engineer are starting to have more distinct roles. Build times are generally shorter, and materials are being estimated and procured based on the design drawings.
We see this in structures like the Eiffel Tower and the Woolloomooloo Finger Wharf in Sydney. And blueprints are becoming more commonplace.
Another step in that evolution. And then just 25 years ago, drawings were still frequently hand-drawn, but the roles of architect and engineer were becoming even more specialized. Computers were being used for specific engineering analysis tasks.
We see the early adoption of analysis software, but it's still quite isolated. It's not yet integrated into the design process in the way that it is today. And although materials are being estimated and ordered in advance, a lot of those quantities are still being measured manually from the drawings.
So there are still these manual bottlenecks in the process. And then, 15 years ago, CAD has become the dominant tool for producing construction drawings, and computers are capable of much more complex analysis, things like finite element modeling. But again, the quantity takeoffs are often still done by hand from those CAD drawings, and this is where BIM comes in.
It addresses those bottlenecks. It integrates all those different aspects of the process.
Right, so for anyone who's maybe less familiar with the concept, what exactly is BIM?
Our presentation defines it as a digital representation of a facility's physical and functional characteristics. It's a shared knowledge resource that provides a reliable basis for decisions throughout the entire building life cycle, from design to construction to operation and maintenance.
And it's not just a 3D model.
Right, it's much more than that. The 3D model is sort of the heart of BIM, but it's embedded with all this data about every component of the building. It allows for a much more comprehensive and integrated approach.
So it's like a digital twin of the building, and what are some of the key benefits?
Well, for designers, it offers incredibly powerful visualization and coordination tools. Because the documentation is directly linked to the model, any changes are automatically updated across all the drawings and schedules in real time.
No more manually updating multiple sets of drawings.
Exactly. It also integrates modeling and analysis. Whether you're doing structural analysis, energy performance analysis, whatever it might be, it all happens within that same BIM environment. It saves a huge amount of time and eliminates the need to create separate models for different purposes.
So it's about streamlining the workflow, reducing redundancy.
It is. And that coordination aspect is a game changer. BIM allows you to overlay the architectural model with the structural model, the MEP model, all those different systems, and identify any clashes or inconsistencies in a virtual environment.
You're basically doing a virtual construction before the real one begins.
Precisely. You can spot those potential problems early on and resolve them before they become costly issues on the construction site. That ability to proactively manage coordination is a huge driver of efficiency and cost savings.
And what about the builders? How does BIM benefit them?
Well, for starters, it allows for the automation of accurate quantity takeoffs. No more manually measuring from drawings. The model contains all that information.
So you get a more precise estimate of materials needed.
And less waste. It also enables the automated generation of shop drawings for fabrication. You can even simulate the entire construction sequence within the model.
You can literally see how the building is going to go together step by step.
And that has huge implications for logistics and cash flow. And of course, that coordination aspect we talked about benefits builders just as much as it benefits designers. The example in our presentation of those coordinated building services really highlights how powerful this can be.
I mean, being able to virtually walk through a building and identify a conflict between a duct run and a pipe before any physical installation begins, that's got to save a lot of headaches down the line.
It does. It's about avoiding rework, minimizing those costly surprises on site.
And ultimately, it benefits the client, the people who will actually own and use the building.
Exactly. BIM gives them better visualization from the beginning, so they have a clearer understanding of the final product. That leads to better design outcomes and fewer changes during construction. And it also leads to those cost savings we've been talking about. Fewer errors, fewer delays, fewer cost overruns.
So it's about transparency, predictability.
And perhaps most importantly for the long term, BIM provides the client with this rich digital model that can be used for ongoing facility management and operations throughout the building's life cycle. It's a valuable asset.
So it's not just about the design and construction phase, it's about the entire life of the building.
It is. It's a much more holistic approach. And our presentation really emphasizes that BIM is no longer some emerging trend. It's becoming the industry standard. It's the benchmark for major projects. It's widely used for medium-sized projects. And the feedback from the Sydney construction market in particular suggests that professionals who don't have BIM skills are increasingly at a disadvantage in the job market.
So it's not just a nice-to-have skill anymore, it's becoming essential.
It is. And it's part of a broader industry trend towards this idea of a data-rich model as the central source of truth for the entire product lifecycle. Our source even mentions PLM, product lifecycle management, as a multi-billion-dollar industry that's impacting how engineering design is practiced across many sectors.
It's about managing complexity, leveraging data to make better decisions.
And it's interesting to see how far we've come. Those early limitations imposed by computing power, they've largely faded away thanks to the exponential increase in processing capability. Software is now robust enough to handle the complexities of most design challenges. The focus now is on effectively managing and leveraging the vast amounts of data that are generated in these increasingly complex projects.
Like we see with Airbus and Boeing and their experiences with digital design and manufacturing. So as we wrap up this deep dive into the evolution of building documentation, I think the key takeaway is this. From those initial hand-drawn sketches to the intelligent, data-rich 3D models of BIM, the way we design, document, and construct our buildings has undergone a truly profound transformation.
It's been an incredible journey, and it's still unfolding. And it makes you wonder, what's next?
Exactly. What new possibilities and perhaps unforeseen challenges might emerge in the next 25 years? How will technologies like AI and virtual reality further revolutionize the way we conceive, create, and interact with our built environment? It's an exciting time to be in this field, that's for sure.
Absolutely. It's a constantly evolving landscape.
Well, thanks for joining us on this deep dive. We hope you found it insightful. Until next time, goodbye.